All right, so next we are starting on inverse functions. And this is a really important concept that you will see over and over and over again. We'll see it particularly in chapter, I think it is 6, when we start talking about exponential functions and logarithms, but also some in other places in this course as well. You'll see it in trig, you'll see it in calculus, you'll see it in any other math classes that you take. So we want to be able to verify whether a function has an inverse, whether a function is the inverse of another function. We want to be able to determine the domain and range of an inverse function, learn how to restrict the domain of a function to make it so that it can have an inverse function, find, evaluate the inverse of a function, and graph the function. Use the graph. So these two are flipped. Always a typo. Okay, so first off, we're going to start with a definition. We have what's called a one-to-one function. So we say a function is called one-to-one, and usually I will write 1-1 if each output corresponds to exactly one input, so one and only one input. Okay, so in other words, if your two inputs are different, then your two outputs are different. They're not equal. So a function is one-to-one if f of a is equal to f of b implies that a equals b. So in other words, if your outputs are the same, are equal, if the inputs, then the inputs are equal. Okay, so if it doesn't meet that, it's not one-to-one. So we're going to prove this algebraically, or show this algebraically, by doing just basically what we said. So we're going to say, hey, let's pick a point A, and we're going to plug that into the function. We're going to get cube root of A. We're going to pick a point, unknown point B, it doesn't matter, it's just generic, and f of b, cube root of b. Now, so basically, if the outputs are the same for one-to-one, so we're going to assume f of a equals f of b, so that would mean cube root of a is equal to cube root of b. And we need to kind of solve, get rid of the cube roots here. So we're going to do that by cubing both sides. Actually, I want to stay that. So cube root. And what we are going to do is we are going to say, hey, I'm going to cube both sides, because that will get rid of the cube root, right? And for this one, if you cube a cube root, you get a. There's no ambiguity like you have with square root and things like that. So if we assume that f of a equals f of b, then the consequence of that is that the input has to be the same. A has to be equal to b. We can do the exact same thing with our function on the left-hand side here, the linear function. So we've got f of a, 4 minus 2a. We've got f of b, 4 minus 2b. We're going to set those equal to each other. So we're assuming that they're equal. So we're going to do that. We've got 4 minus 2a equal 4 minus 2b. Of course, the 4's are going to cancel, right? Minus 4 minus 4. Negative 2a equals negative 2b. Divide both sides by negative 2. And we end up with a equals b. So therefore, it is one-to-one for both of these things. Okay. So what about this one? All right, this time we've got f of x equals 3x squared plus 1. So we saw two examples where we did prove that it was one-to-one. You might suspect that this one we're going to not be able to show that. So let's see if we can actually write. So we're going to have f of a. We have 3a squared plus 1. We've got f of b, 3b squared plus 1. We're going to assume we're going to let f of a equal to f of b. So we've got 3a squared plus 1 is equal to 3b squared plus 1. Of course, the plus 1s are going to cancel. All right, so we'll just say subtract 1 from both sides. Divide by 3 to get a squared equals b squared. Now here, we are going to take the square root of both sides to get rid of the square because we need to solve for a or solve for b. And the problem here is when you take the square root, you get two possibilities, right? The square root of 4 is equal to plus or minus 2. So this, the same output, has two different possible inputs. It is not one-to-one. So for equal, so let's put it this way. Same output can be gotten, there we go, from two different inputs. So that means it is not one-to-one. I'm going to go ahead and go to the next slide, and that will make a good stopping point. And that is because showing that a function is one-to-one algebraically is a pain in the butt. I might ask you to do it on the test, and I do want you to do something similar to what we just did. But there's a much easier option, and that is the horizontal line test. So we can determine easily if a function is one-to-one by looking at whether or not there's any horizontal line that can be drawn that intersects the graph of f of x more than once. If it can, it is not one-to-one. So this is like the vertical line test, but horizontal. So we have a function is one-to-one. It has to pass the vertical line test to be a function, right? And the horizontal line test to be one-to-one. So that's kind of like a, if it is a function, then we can see if it's one-to-one. So for example, let's suppose that our graph looks like this, right? That's like a cubic. And this is not a one-to-one function because if I draw, there's numerous horizontal lines that I can draw that intersect the graph in more than one spot. But really, this is doing the same thing as what we just did algebraically, right? This is, we have the same, this might be f of a, this is f of b, this is f of c. They're all equal to the same value, right? But three different inputs give us that same output value. So this is not one-to-one. A graph that might look like, let's say like that. On the other hand, every horizontal line that I might put through here only intersects the graph in one spot. So every input has one output and every output has only one input. So, and as a side note, a function that's strictly increasing, or always decreasing, strictly decreasing, over its whole domain is always one-to-one. So that's a good place to stop. We'll have some examples and move on to other topics.